Exciting day on theory of games and toys and art and everything else. We are delighted to have Sir Keith Moffatt to kick off the day with the beaver ball and a chaotic rolling robot.
Yeah, thank you, Jane. There's no sir as yet. But anyway, lovely to be here, and thank you, Angie, for organizing a wonderful workshop so far. It's been terrific. I've enjoyed every moment of it. So it falls to me to start off the session on toys. Toys are wonderful in some ways as a connection with the general public in outreach, and particularly with children. Of course, you can fascinate children with toys and somehow get across to them that there's something really intriguing about toys that have some interesting mechanical content, as the beaver ball has. I was in Toronto, actually, at the Fields Institute. It was about 2 years ago, I think, maybe 3. We were having a meeting commemorating what would have been the 75th birthday of Arnold. And Vladimirov was there, my good friend and colleague, who's now working in Oman at the Sultan Qaboos University. He was there anyway, and we took a walk down the road towards Chinatown, and there was a toy shop there, and we saw this beaver ball being demonstrated, and it looked intriguing and interesting.
I walk by that thing every day, practically.
You do, so you know it.
He's going to talk
You
about
lucky man. They probably have all sorts of interesting toys, other ones there from time to time. But it was the first time I'd seen it, and I thought, oh, we could. I think, well, I want to understand how it's made firstly. So we had to buy several and cut one of them open. And look, well, you can unscrew it, so it's all right. Find out how it's made and what activates it and how it behaves in the way it does. Well, I'll demonstrate that to you in a moment. But anyway, that's how I came across the beaver ball with Vladimir, and we roped in his younger colleague, Kostya Ilin, who's at the University of York, and he's been very, very good on the computing side and on the general mathematical background as well. So I thought it would be appropriate to tell you about this. It's just actually been published, our paper on this topic in PNAS. Now there's a good reason for my using this backdrop here. This is in the antechapel of Trinity College, and you'll all, I'm sure, recognize this as the statue of Isaac Newton by Roubiliac, the French sculptor who was living in London when he created this masterpiece. And I wanted to do the experiment with the beaver ball, which you see here on the floor, because it's a nice horizontal floor and reasonably smooth marble floor, and it was the best floor I could find for this experiment. So this is my laboratory. I think I'll play it right away. I call this one the dance of the beaver ball. There were always a few tourists around, and there were on this occasion, and there were 2 children in particular from Japan, and they were quite intrigued by this, and we were quite lucky because there was a music rehearsal going on in the main chapel at the time I did this. So let's see if I can activate this. Oh yes, I know. I can do it when it's. Oh, here we go. Okay. And let's see, there we go, yeah. Well, I've got not the one I wanted. Let me go back one place. This is the one I really want, if I can make it. Yeah, there we are, and we got the music. And if you haven't seen the beaver ball before, you'll be wondering You'll be wondering what is going on exactly. Volume. See, actually it does keep time to the music, which is rather nice. Well, that's obviously intriguing. It seemed to be a fairly chaotic trajectory. I'm sorry, halfway through that, as you see, I turned the camera on its side to get a better view, and I forgot that I was unable to then edit the movie to rectify it, and that's why you see it the way you do, but I think it was still quite understandable. Now, let's go to the next one. They're just a little variety of... so here's a fairly typical movement of the ball. It seems to be going in a fairly large circle. Under the eyes of Isaac Newton. You hear me there? I was describing this to one of the tourists who's on the side, and well, it's trying to do a circular orbit, but with oscillations, and it's drifting a bit. It's actually a fairly chaotic path, but with a certain persistent rotation. Okay, and here's a different ball, but and that one we started off. It spun for some time on a spot, but then something unstable about that, and it moved away, and again began to follow a more circular, perhaps you might say slightly spiral path, slightly increasing radius, and I think I have one more, well, a close-up here to try and see if we could detect anything. Now that, a little wobble and a fairly straight line. It hit a boundary, but it doesn't affect it. It just moves off and keeps going. Wonderful. Oh, okay, well, here's the abstract which you'll have read, and it's a little, I hope it wasn't off-putting, it's a little bit heavy mathematically, but I will skate through the mathematics because I'd like to describe this, the mechanism here, but also, if time permits, I'd like to mention one or two other toys that I've been involved in over the last 20 years or so. I mean, I think of myself as a fluid dynamicist, but toys are fascinating, toys of this kind, and you can't help being drawn into this sort of analysis, which is really very classical applied mathematics, the sort one learns at university. And I remember learning all the principles required for the solution of this problem in the 1950s. I was a student at Edinburgh University, and that's where we learnt analytical dynamics. I don't know if it's taught quite to that level. Rigid body dynamics now in the Tripos. Okay, well, you see immediately when you draw the diagram that there's something complicated about this. The ball is actually activated. We can play with these afterwards. It's activated. You can unscrew the two halves, and you find that inside there is a rotor fixed, which is driven by a battery, and the rotor simply rotates on a spindle which is attached to the shell, and of course the ball then rolls on the floor without slipping, and so the spindle that it's attached to is moving all the time, and the rotor is rotating all the time about this moving support. So this is what is complicated about it. And I think you see here, we've tried to give you a diagram of it. Here's the floor. Here's the point of contact, C, where you have a no-slip condition, as in fluid mechanics, in fact. But this point C, because it's no-slip, it means that the point C of the spherical shell is instantaneously at rest. which always takes people a little bit by surprise. And here is the rod, which is fixed to the shell at A and B, but free to rotate about its own axis. So it's on the bearings at A and B, which are very well constructed. And this is the rotor, which rotates. It really is a little machine that rotates, driven by its battery. But we've modeled it here as a point mass. It's not perfect modeling, but it's the obvious sort of thing you do when you're in applied mathematics. You try to reduce the problem to its essentials. So we're at a distance d from the center, less than the radius a, and then the mass here is at distance b. So this is fixed, right angle. That is a rod fixed to the rod AB. So the shell has mass m, let's say, capital M, and the mass little m is at the point P. That's our model. The internal battery causes dP to rotate about AB with constant angular velocity, sigma. The shell rolls without slipping on the floor, and the problem is determine its motion. Now, it's the sort of tripos problem that James Clerk Maxwell might have set in the 1860s, because he knew how to do this sort of thing. But it's, I think, too difficult now. That's the advance of science over here. It's difficult because the orientation of the rod changes as the ball rolls. And for this reason, the equations of motion are best expressed not in an absolute frame of reference, but in the body frame of reference. I've called it O prime, X prime, Y prime. You see O prime at the center of the sphere, and then you've got X prime, Y prime. Z prime is along the axis here, and X prime, Y prime perpendicular. And so this is rotating in an unsteady manner. That's rather nasty. It's a little bit like the Earth when you think of it. The Earth is rotating, spinning, and precessing and nutating a little bit. And there are all sorts of forces that come into play. Coriolis forces, and another force which actually appears here called the Poincaré force because of the unsteadiness of the rotation. Well, there are 4 dimensionless numbers that characterize this. The ratio of the masses, mu, this parameter related to gravity, a sort of dimensionless gravity, so gamma, g over sigma squared a. This is then a pure number. Beta, and then 2 geometrical numbers, b over a, the radius of the sphere, and delta, I've called it d over a. So 4 parameters for this problem, fairly rich, you might say, in possibilities. And then you have the rolling condition. Point C, as I said, is instantaneously at rest. There's no slip. So the velocity of the center point plus omega, angular velocity, cross with this vector to the point C is 0. This is the velocity of the point C, and it's 0. That's the rolling condition. There's also a contact condition. See, if that mass spins very rapidly, then occasionally the centrifugal force upwards will be greater than gravity, and it will lift off from the, you'll get a sort of levitation effect. Oops. It will lift off from the table or the floor, and so gravity has to be large enough. It's you can estimate it in this way: 1 plus mu times gamma, the gravity parameter, must be greater than, I put a roughly greater than mu beta. That can be made more precise once you've actually solved the problem. Then there's the fundamental quantities that one has to consider. The linear momentum, mv, so that's mass of the shell times the velocity of the center, plus little m vm, so that's mass of this mass here, times its velocity, vm. And then there's angular momentum. I've called it L, and I won't labor the detail, but you can figure. The I here is moment of inertia of the spherical shell, which is very simple. 2/5 m e squared, something like that, 1/3. I can't remember, for a shell, anyway. And there are these other contributions. Okay, so then you have these, and you then can write down the equations of motion. And it all gets a little complicated. There's rate of change of momentum and rate of change of angular momentum. This is the total force acting on the body, on the ball, and F is the force exerted by the floor on the ball, which is normal reaction plus a frictional force, tangential, that prevents slipping. And the angular momentum is the moment of the various forces acting. This is in an absolute frame of reference, but one can manipulate these equations, and it's quite a bit of manipulation, and ultimately reduce it to a system of equations that I've indicated here. These are equations with the hat on and they're dimensionless equations, a dimensionless time, tau rather than t, in the body frame of reference. So you've got an angular velocity which is changing with time, and then you've got the vector to the point C, which in the fixed frame, the inertial frame, it's of course constant, but in the body frame, that A is changing with time, and tells you just what the orientation of the body is at any time. So you've got, and then B is the vector in the body frame to the mass, and that's prescribed. That's the one little helpful bit of input here. We know what it is in the body frame. We don't know what it is in the absolute frame. That's why we have to use the body frame, and this is the prescribed motion of the mass. Now, this can be generalized. You could have any number of masses as long as their motion is prescribed. You know what they are relative to the shell, then this method will work. There is a tensor coefficient here, which is a bit unpleasant. This is related to the moment of inertia, and this is what it looks like. There's a vector S, which is B minus A, and there is actually just one little, the silver cloud, silver lining to this cloud is that there is one integral, obvious integral of well, let's see, I don't think I've written down the second equation. Yeah, here it is. This equation here, and it is that the length of this vector is constant. We know that anyway. But it's nasty. It's a sixth order nonlinear equation. It's actually a cubic nonlinearity. You can see a cubic term here, the omega squared times an A. So nasty. And there's more cubic effects in here. And it's non-autonomous in the sense that there is a forcing in here dependent on time tau. So you can make it autonomous by making it 7 degrees of freedom if you like, if you prefer. But 6 with one integral. So that's where we are. Now, that isn't enough because conveniently the x doesn't appear in these equations. You can integrate them in principle with given initial conditions. In principle, I say, you've got to use the computer to do it. This is a subsidiary system to determine the actual trajectory of the ball on the floor, determined by a vector x. These are unit vectors, again, in the body frame, and if you integrate these and then these, then you've got equations. And this is a relatively straightforward, I would say, to determine. Because you know the rolling condition. If you know the angular velocity and the of the sphere, then you can figure out some way to determine the actual trajectory of the ball. So that's the background, and then it is a question, I'm afraid, of resorting to the computer. And these are various figures that we produce. I think I've lost the caption for this one, but it's not very interesting. These are the actual trajectories of the ball under different conditions for different choices of the various parameters. For example, here in this I guess this is oh yeah, I think this is a figure. No, that's the caption for this one here. The caption here, figure 3, for this whole figure, tells trajectories of the ball center. Mu equals 1, so the two mass is the same. Gamma equals 1, the gravity parameter. I mean, you can choose them anything you like. That's the nice thing about mathematical modeling. Of course, for the ball itself, these parameters do take very specific values. Now, I can come to that. Rho, I can't remember what rho is. It's related to these geometrical parameters, though. I think it means you're halfway. The mass is halfway between the center and the boundary of the sphere. and so on and so on. We did work out Lyapunov exponents for the cognoscenti here. We'll know what I mean by this. When this Lyapunov exponent is relatively large, that's like in C and D compared with A and B. In C and D, you expect chaos. When it's small, you expect regularity. Well, really, it would have to be 0. If it's non-zero, then, well, it's an indication of chaos. This doesn't look chaotic, but it probably is after a very long time. Likewise, that doesn't really, it looks as if it's moving, but it looks as if there's a considerable regularity. This is the center of the sphere that's moving in some kind of epicyclic motion, basically a circle but with large oscillations. As we observed generally when we did a fairly random and uncontrolled experiment. Then this is just varying initial conditions. You see same initial conditions given by this and this, which is not very helpful, I'm afraid. But you don't have to worry, different initial conditions. And here are trajectories. Here the initial conditions are given. Mu is 2 now, gamma 4. So we varied these and the geometrical parameters and got a variety of rather beautiful, sometimes regular, sometimes chaotic, and sometimes slightly indeterminate. It's hard to tell. I was actually struck when Yves Couder gave his lecture at the beginning of one of the earlier workshops, I think it was, or one of the seminars in this program, on his wonderful work on bouncing droplets on a bath of silicon oil that's oscillated vertically with a prescribed frequency. And pictures rather like this and this and this do come out of that sort of work. And the similarity was rather intriguing. And I wondered, I mean, this, of course, is a rigid body with activated by, again, a prescribed frequency agitation inside. But in a way, there are some similarities because you've got the prescribed frequency interacting with the global motion, and the global motion reacting back on the prescribed frequency. This is, for us, the wave-particle duality situation. Well, of course, we immediately began to look for the sort of effects that Yves has discovered, the quantization of orbits, for example. And we haven't found such a quantization as yet. But there's a lot of exploring still to be done. So there, I think, finally is perhaps figure 6, more examples. You see where the ball starts its trajectory and where we stop the computation. And this would just go on and on for a very long time. And in every case, I think green is where it starts, red is where we stop the computation. This last one is with parameters that refer to as for the actual beaver ball, the one that you purchase either in Toronto in that toy shop or online. It comes from China, the one I got online. Mu is 4.6, near enough. Gamma 3.2, beta 0.5, and delta is actually 0 in this beaver ball. It's the rod dp is mounted. The point D is at the center of the sphere. I think making that parameter non-zero has quite an important effect. As you might expect, it's a significant perturbation. It may be that when the delta is very small, one could do some kind of interesting analysis. We haven't done that. We haven't tried that as yet. It's all really very complicated. And A shows you a trajectory here that's obviously pretty chaotic. It starts with M, the mass, the internal mass, near to the highest point. You can manage that some, although you can't see inside. You can figure out where it is and just start the ball rolling. With 0 angular velocity, you place it down at the highest point. Well, that's unstable, that highest point. You start here, it's unstable, and it goes off on some kind of chaos. And as far as we computed, now that tau being 300 pi means about 300 oscillations. 300 oscillations, roughly speaking. It hadn't settled down. It may settle down to something like a circular orbit, but you'd have to compute for a lot longer. And secondly, B, we started with the M being near the lowest position, which you'd think would be stable. But of course, because of the rotation, it sets it rolling, and it sets it off on a trajectory. So it goes in a fairly large circle, but with oscillations, and it looks again fairly well, you might say pseudo-periodic. Periodic one way with an additional periodicity going around this way. Boris Kessin, when he read this paper, he made an interesting comment. He said, well, this looks a little bit like as if you might have something like KAM tori. And although this is a non-Hamiltonian system, it's possible that there's an analog of that. If you have an orbit which is definitely regular, if you hit the exact right conditions, then when you're near that orbit, it may still have regularity, as described by Kolmogorov, Arnold, and Moser a long time ago. But again, that seems to be a point that would be well worth exploring if we can engage Kessin with his very considerable knowledge of this field. Well, I'll just show you the few references that we made in this paper. I should mention Chaplygin, because that's, you see, 1897. All the principles were known at that time. He wrote down the generalized equations that would treat a non-holonomic system of this kind using the analog of Lagrange's equations, but with additional constraints, non-holonomic constraints. And we tried to use his equations when we started on this problem, but we found it exceedingly complex. And we found eventually that it was easier to go back to the fundamental principles, linear and angular momentum, and as I've described it to you. And then these other references were the ones we used. This reference here, which is very useful for the calculation of the Lyapunov exponents for each of these computer runs that we did. And this paper is relevant as well. We always, of course, have acknowledgements at the end of a paper. Vladimirov acknowledged his support from the Sultan Qaboos University. And we thank 3 referees for their valued comments. And here I should say that I have inside information that Angie was one of the referees of this paper, and so I'm most grateful to him for the very favorable comments and suggestions that he made. Well, how's my time? Have I got 5 minutes more, perhaps? Or
You got 1 minute, I believe. Oh, wait a
No.
minute.
10 past.
maybe I've got 10.
It's 10 o'clock. And so
Yeah,
which means,
what's the schedule?
oh yeah, you have 30 minutes.
No. You have 7 minutes.
7. She's a wonderful chairman.
I was so absorbed in your talk, I was not paying any attention to time. And I
And with questions.
7 minutes.
Yeah.
7 minutes.
In total.
7 minutes is just time to mention 1 or 2 other things, and then I'll be very happy to have any questions on that. As I say, I'm a fluid dynamicist at heart, and you may know this wonderful photograph, which I've used on occasion. It's a turbulent vortex ring emitted by the volcano in Sicily.
Etna.
That's the one. Etna, Mount Etna, in the year 2000. And that photograph was taken, a beautiful example of a vortex ring puffed out. This is the sun trying to illuminate. This, yes, I just wanted to mention as one of the, since we're half art in mathematics and half toys, I wanted to show you this rather beautiful photograph that was taken by Ray Goldstein. He's just left, I think, and he would have been intrigued to see that I'm showing this. we collaborated on a piece of work that led to this wonderful photograph. It involved the collapse of a Mobius strip soap film, and you can imagine the fun that one can have with that. Let me see if I can. This is the film collapsing. Oh, both of them are going simultaneously. That's wonderful. So you see the one on the left is a standard collapse of a catenoid soap film, and the one on the right is something else. And you see that little twist there, and that was what was so intriguing about this problem. And in fact, that is the same twist enlarged. The whole film, soap film, is twisted quite strongly in the neighborhood of this point here, and it's associated with the twist of the plateau boundary, as it's called, around the wire. You can see it coming down here on one side, twists around the back, and re-emerges down here. And the surface is twisted in the same way. Well, I just wanted to show you that. And also to show you this sort of picture, which, you know, is such a long and wonderful tradition in Cambridge, starting with Stokes himself of the Navier-Stokes equations. Kelvin, who was a student here before he ended up in Glasgow. Tate, likewise, student here, he ended up in Edinburgh, and James Clerk Maxwell. They let's come to more recent times, nearer to mine. I was brought up on Lamb's hydrodynamics. He was, all these four were fellows of Trinity College in their time. G.I. Taylor, a very famous fluid dynamicist of the last century. My own supervisor, George Batchelor, who founded the Journal of Fluid Mechanics in 1956, and James Lighthill, Trinity College, also during the 1970s. Well, that's very brief. Now, other toys. The rattleback is one, and I wrote a paper with, let's see if I can get it to, there we go, yes. This is the University of Cambridge version of the rattleback. I wrote a paper with Tadashi Tokieda, who'll be here tomorrow to give, and he usually gives a wonderful lecture on this sort of topic. But the point of the rattleback is that if you rotate it one way, it's perfectly happy. And if you rotate it the other way, it's perfectly unhappy. It reverses its direction. And we described this as a well-known phenomenon. It was identified first in the 1890s by a man called, I think it was H.T. Walker, who later famous for the discovery of the ENSO, the Indian Ocean Oscillation, oceanographer. But before he went off to the Indian Ocean, he was intrigued by this sort of problem. He wrote papers on the boomerang as well as the rattleback. And he recognized this problem, but he didn't solve it. And there have been a number of papers since then, but I believe we gave the simplest explanation of what is involved. This is the Russian version of the rattleback. You can deliberately impose a chiral perturbation, and as Tadashi would say, turtles like to go forwards. Generally speaking, they're quite happy. You see, a little reversal at the end, but they do not like to go backwards. They're very unhappy if you try and force them to go backwards. Well. Let's go. We managed to develop fairly simple equations describing this phenomenon. If there's no dissipation, then it's actually, look at just this curve here. It's a periodic phenomenon. You get a plus, minus. It's a strong reversal, and then another much weaker reversal, and then a strong reversal, weaker. It's periodic if there's no dissipation, conservation of energy. But there is dissipation, and that transforms things completely. You get a strong reversal, and then if you're lucky, you might see a little reversal here, but Normally you just don't notice it. So that is the toy rattleback. Well, then there's the problem of the rising egg, which is equally intriguing but entirely different. I say I'm interested in these problems because each one there, you spin it and it rises on its end. Sometimes I would say on the sharp end, sometimes on the blunt end. There it's on the sharp end. And I wrote a paper on that with Shibamura in 2002. It came out in Nature with a rather nice headline, which was this: an explanation for an odd egg performance is rolled out in time for Easter. It was published just before Easter in that year, 2002. So that took some explanation. But as Dennis Ware mentioned the other day, this is governed by something called the Gellert constant. And the thing is, the difficult thing is to identify that constant and its relevance for this problem. But once you've got that, the fact that it rises is it's minimizing its energy subject to conservation of this Gellert constant. And that is enough to explain this behavior. And lastly, you'll be happy about that, is the Euler disk, which was the first toy that I was interested in. If I can get it to spin, then we can end on that. I put up the sound for this one because sound is important. You can hear me whispering to myself. I wasn't aware I did that. This will last for 90 seconds, and then I stop. So you can hear the frequency goes up, which is a little bit astonishing. You think, well, the energy must be decreasing. There's dissipation. But the frequency goes up. So the point of contact with the substrate is rotating faster and faster. This can't go on forever. It is approaching a singularity. A singularity at a finite time. There. Finite time singularity. We're terribly interested in that in fluid mechanics at the moment. Do the Navier-Stokes equations admit a finite time singularity or don't they? Famous unsolved problem. I think it's always helpful if you talk to students about this to have an example like this of a finite time singularity that can be demonstrated in this way. Well, my time is up, I'm sure, so thank you very much.
I guess you know that these beaver balls, you can buy them with tails.
Yes. In fact, you can't buy them without tails. You have to cut the tail off.
Yeah, there you go.
That's the one. Yeah, and of course, the reason for that is when it rolls around, the tail flaps around. And it really is little kittens that enjoy this. They chase it. They think it's a mouse. They think it's a reel. Right. And they love it.
The one in Toronto has been rolling in that box for years.
Has it really?
Yes, and it had a tail originally, but it eventually came off. But the box is starting to wear out. You can see the path of the thing on the inside of the box. On the pavement outside of the store.
Yeah.
And literally every day it's rolling.
Is that right? Yeah. It attracts people into the shop, of course, to see the other things. Yeah. Daryl.
Keith, I had a student for his project, his third year. He did the Euler disk, and he went over to mechanical engineering and had a hole drilled through it, off axis.
Oh.
Okay, and it did the rising egg as well. It oscillates.
He did the rising egg.
No, he didn't do it.
He did.
So when you rotate the Euler disk with a hole drilled off axis,
yeah, what happens?
it goes up and down like that.
Oh, right.
So it
Interesting.
has a rising edge
That's nice.
phenomenon.
Okay, I see. But eventually it's, of course.
Yeah, of course.
Good.
You said that when delta isn't zero, there are significant differences. That wasn't obvious from the picture because you still had
Oh, yeah.
is it chaotic motion or regular motion.
Yes.
But my question is, when delta is zero, is that any significant simplification? Is there another constant of
Not
motion, for
really.
example?
Not really.
Not-
No, it isn't. There's no other, we couldn't find any other constant of the motion.
Last question. Dennis?
Small suggestion from someone obsessed with the game of rugby. It would be fairly easy to take a beaver ball and put an ellipsoidal shell around it.
Yeah.
Have you considered that?
Well, we have thought of it. I mean, in principle, one can do this sort of thing. It just complicates matters considerably, of course. But yeah, that would be rather, it would be interesting because you'd get the more interesting rolling. You could patent that, and if you can make it. Well, you could make it. I know you can.
Very
make it. Easy to make. Yeah.
It's really printing.
Existing beaver ball, you just put a
Yeah.
shell around it.
Yeah.
Because the clock is this way. Well, thank you, Keith, and thank you for being on time. And,
Thank you.